Hello everyone, welcome back to the latest lecture session. In the last session, we looked at understanding theta c and relevant variables, right? And in this session, we are going to pick up where we left in the last session, namely, we were discussing food to microorganism ratio, right? And how is that relevant to our system? That's something we will look at now, right? Let's see what I have here. So, it's food to microorganism, right? Food can be based on S naught, what is coming in, or what is coming in minus going out. So, depends on what is it, who or which textbook or such people look at. So, it can be something like this, microorganisms in the system, or as I mentioned, you can just have QS naught by Vx2. So, that is one aspect to keep in mind, okay. So, then what is this giving me an idea about in the first case? It gives me an idea about the kind of bacteria that can thrive and thus the kind of flock or settling characteristics, let us say, right. Let us look at it. So, here we have two figures. A variation of this figure, we looked at it earlier, as in that figure was somewhere like you had this lag growth phase where you had acclimatization and such, and then remarkable level of growth and relatively uniform growth and then stable and then decay, right. So, we had different stages there. So, again this is a variation of that figure. So, what do we have here? Characteristic growth phase of a pure culture of bacteria, and this is when we have substrate. Let us say substrate is somewhere out here and substrate or the food is being consumed, right. So, that is what you have out here. It is something like this. So, if there is food available, and that is how it is going to decrease. On the y axis we have concentration of biomass or the microbes. On the x axis we have time and also some information about the substrate available, let us say, right. So, here I have a lot of substrate and this is again in a pure culture, as in there is no inflow, no outflow. So, initially microbial concentration is very less and or it is x naught, and there is an acclimatization phase and then an exponential growth phase, right. And then you are going to have what do we say, log growth or such, where you have uniform growth characteristics, and then you are going to have declining growth phase and then stationary and endogenous. Somewhere out here you see that almost all the substrate is 0, let us see, right, and initially substrate is the maximum. But how is this still occurring? Here we have endogenous respiration, right, stationary phase and endogenous phase, as in the cell mass of the relevant microbes are being consumed, let us say, for the microbes to be able to survive, let us say, endogenous respiration. So, that is one aspect to keep in mind. Here though is that as bacteria die, or I think bacteria reach this endogenous phase, they give out a slime layer. I think we have the pictures again from MIT Open Courseware. So, these slime layers, I guess, help in forming flocks and maybe the bacteria sticking together, if I can use layman's terms. So, if you can see to it that your particular microbial population is in this phase, you are going to have good sludge and sludge settling characteristics. So, that is what we see here. So, here we have on the x axis food to microorganism ratio, and here on the y axis we have rate of metabolism, right. How fast are they, or how well are they metabolizing, right. So, what do we have out here? So, in the exponential growth phase, right, firstly the settling characteristics are going to be poor. Here we have higher F by M and higher metabolic growth rate. What happens when you have higher food to microorganisms ratio? Let us just understand that before I think before we look at that in detail. A lot of food and less microbes, right. So, there is food everywhere. So, the kind of microbes that are going to have or that are going to thrive are what are called as motile microbes, let us say, right. These can move based on their, or they have a free will, if you can say so, and they can move in search of food, let us say, right. And so, these form flocks which are called pin flocks. I think we looked at some such figure earlier when we were talking about settling or sedimentation, pin flocks, and they do not settle well, let us say. So, that is one aspect to keep in mind, poor settling characteristics, let us say. And also because the food or R waste is pretty high in this relevant system, it is also going to leave the system through my effluent. So, some of the or the concentration of the waste in the effluent is going to be relatively higher. So, that is one aspect to keep in mind, F by M here, let us say, right. So, this is something that we do not want. So, if the F by M is too low, right, F by M is too low, again you are going to have different kinds of issues with respect to sludge bulking and such. So again, as I mentioned, we want that sweet spot where we have the slime being formed, and I guess it's between this declining growth phase and this endogenous growth phase, let's see, right? And this is the range of operation that's ideal. So that's what we have out here, and you see that the F by M is not too low, but it's certainly not too high, right? So that's something to keep in mind. Let's move on. So high F by M ratio meaning high food, right? So they grow fast, and slime layer is thin. Again, here we are talking about, I think, the exponential growth phase. That's something to keep in mind. We have motile bacteria, and they have high energy to swim to food. Thus pin flock, right? Poor settling in secondary clarifier. First, poor settling and also high food. So both ways, not a great aspect for us, I guess, right? So excess food is carried away, treatment efficiency is poor. By playing around with the variables, we can get this. We looked at this in terms of X and so on and so forth. Y is that yield coefficient. E is the efficiency of removal, S0 minus S by S0 into F by M, right? F by M minus KD, let's see. So what do you see here? When F by M is high, right, theta C will be less, or the cell residence time will be less, right? F by M, again, if that's one aspect to keep in mind. So if I keep the cell residence time the same, and if I increase the F by M, what will happen? The efficiency of the process obviously will have to come down. So that's something to keep in mind. If I increase the food to microorganism ratio, the efficiency will come down. So right, efficiency is this. So that's something to keep in mind. And with low F by M, what is it that we see? Low F by M meaning low food and more relatively more microorganisms. Again, everything is relative, let's say. So the microbes are starved now, right? They are pretty hungry. There might be some endogenous respiration, but we are not at the phase where there is only endogenous respiration, because you are still providing the R waste or the food or the substrate, right? So that's one aspect. So what's going to happen here, right? So undergoes or starts to undergo or experience endogenous respiration. So a lot of relatively high deaths and more predatory or predation, let's say, and so KD is increased, let's say, right? Nearly all substrate is consumed, so thus we have high treatment efficiency. I think we also saw this, 1 by theta C is equal to yield into efficiency into F by M minus KD. That's what we saw earlier. So with a low F by M, right, and for the same theta C, keeping theta C the same, you see that the efficiency will increase. That's something to keep in mind. And also, if we maintain it at the sweet spot, we know that there is going to be a slime that's going to be formed, and also you are going to have the right combination of flock forming and filamentous microorganisms. So it results in good settling flock and thus good efficiency in the secondary clarifier. Let's see if we have some pictures. Okay, we'll come by that later. So cell slime layer is thickest at the start of endogenous growth phase, let's see, right, just at the start, and thus that leads to best conditions for flocculation. Slime layers by dying cells may glue, right, it's gluey layer, right, that holds the flocks together. Slime layers are formed when we have dying cells, let's say, right. And for getting this slime layer though, we need to have good aeration for the living cells, or when they were living, to create the relevant polysaccharides that make up the slime, right. So to get to the conditions that can lead to formation of slime or this gluey layer or sticky layer, you need to aerate it well, let's say, right. So that's something to keep in mind. Let's see if we have pictures. Okay, so here we have the bacteria with the relevant slimy layer all around it, let's see, and then activated sludge flocks with slime. So this is the sticky layer that we want or trying to get, let's see, right. That's what we get when we maintain the F by M ratio at a sweet spot. So let's look at some aspects. So high F by M, F theta C is the same, poor efficiency, and typically characteristic of low theta C if we look at it the other way. And low F by M, obviously better and more complete degradation and better settling characteristics if we can maintain the F by M such that just the system is just at the endogenous growth phase. Obviously for that long, relatively long theta c. But what are the issues? For long theta c, right, that means more recycle meaning larger, thus more costlier aeration tank, right. And obviously if the microbes are spending a lot of time and also the substrate removal is more, I need to provide a lot more oxygen, let us say, right. And well, I should not say poor settleability. This is the case when I have a very long theta c, right, but not in general. And high powers, let us say high power, obviously that is from the requirement of more recycle and more oxygen, let us say, right. But if you maintain the theta c and f by m at the sweet spot, you will not experience poor settleability, let us say. Let us move on. So, bulking of sludge, let us say, this is one common factor that ruins many Indian treatment plants or quite a lot of treatment plants around the world. So, you have the aeration tank, microbes are degrading it. It meaning our waste. Once they go to the secondary settling tank or secondary sedimentation tank or clarifier, what needs to happen? You are not going to provide air, you are not going to provide turbulence. You need to provide, what do we say, the kind of bacteria that form flocks and settle down. But depending on the f by m and theta c, you are going to have what do we say, sludge that is not going to settle down, but have bulking of sludge, let us say. So, what is this characterized by? The solids having poor settling characteristics. It accumulates in the secondary clarifier and even can overflow the side walls, right. So, with respect to f by m ratio and its effect on the bulking of sludge. Again, bulking of sludge, unlike what you might have heard from what I have seen or read, let us say, there seem to be various factors that can lead to bulking of sludge. So, one can be filamentous, one can be non-filamentous and such. Let us look at some of the what do we say, factors or variables that can lead to bulking of sludge. So, here we have high f by m ratio, okay, encourages the growth of filamentous microbes like Sphaerotylus and causes bulking of sludge, right. So, that is one aspect and the relevant aspects are given. Low f by m ratio and long sludge age favors the growth of Nocardia microbes causing bulking of sludge and more importantly foaming. I think I have a picture here. Okay, so you can see the kind of foaming out here, let us say, right. Yes, so that is something that you see, fine, or I guess, okay, this is the relevant aspect. High and low. And the high concentration of long chain fatty acids at low temperature encourages excessive growth of these kinds of bacteria, which again leads to filamentous bulking of sludge. And there is another kind of bulking called non-filamentous, when we have low nutrient concentration which favors excess production of slime, and thus you have viscous slime bulking, let us say. So, that is another or non-filamentous bulking, let us say, right. So, that is something to keep in mind. So, I guess we looked at a similar figure earlier and I think we will look at it. So, pin flocks when we had high f by m, I guess, and thus leading to, I guess, small weak flocks, okay. With respect to magnification, I think I do not have that information. Flocks containing filamentous microorganisms probably at the right mix with their flock forming and filamentous microorganisms. So, you see the relevant backbone and the relevant bigger flocks, let us say, difference between this and this set of what do we see, images, right. Let us move on. And so, Nocardia forming in activated sludge basin, that is in A and B. You can see the kind of forming. I guess these are black and white pictures, maybe we can get better pictures later. And the microscopic what do we say, appearance of the Nocardia forming, let us see. You can see the kind of forming and these obviously do not settle down well, right. So, that is something to keep in mind and you can see the difference between the two kinds of what do we say, bacteria or microbial populations, let us see, right. Okay. So, let us move on. So, we looked at activated sludge and the biological process. So, major aspect obviously is design. How do I go about it? So, here based on thumb rules or such, depending upon how much mass load or how much waste is coming in, you have some what do we say, factors based upon which you can choose the relevant volume. In India, I do not think we choose that often. Simple models based on calculation, simple and design variable values, that is what we are going to look at, let us see, right. So let's see what we have. So conventional activated sludge, so primary sedimentation out here, aeration out here. So I think water is flowing in this direction, and then after aeration, after the microbes have degraded the relevant substrate and the right kind of microbes have been formed, here you have circular sedimentation tanks or secondary clarifiers, let's say, right. So that's the relevant process. So here, as can be seen, they have what seems like a sinusoidal flow, so that you have plug flow characteristics, let's say, right. Again, we looked at why plug flow or relatively ideal case plug flow is better than what we say the usual or ideal CSTR, but we are not going into that right now. So design process, one based on loading factors, right, simple methods and complex methods are based on computer simulation. We are not going to that in detail. This too or not, we are not going to discuss this. We will briefly look at it. We will spend more time on this aspect, right. Let's move on. So volumetric loading, let's say volumetric loading, right. This is the mass of the waste or your waste or the substrate or the microbes food that's coming in, and volumetric loading, let's say, right. And you can calculate the volume by choosing the value of volumetric loading factor. We will not look at this. Another aspect is trying to maintain this F by M ratio, as I mentioned, QS naught by Vx or S naught by theta x, and then you can calculate the relevant variables that you need, let's say, right. So this is something we already looked at earlier, so I will not come back to look at this, but based on what you want to maintain of these three variables, you can get the other variables from here. And so in general, SRT 5 to 15, but it depends on the kind of plant, the extent of removal. F by M 0.2 to 0.4 kgs of BOD per kg of MLSs per day. And I think we saw that the bulking was occurring when we were at around 0.8 or such, if I am not wrong, right. Okay, as you see, high F by M 0.8, right, fine. So that's one aspect. So how do we go about it? Choose the F by M and X that you want. From that, calculate the HRT and then calculate the volume of basin, but again we are not going into that. So loading factors, right, and what are the typical values? Theta, X ranges from 2000 to 5000 volatile suspended solids. Typically, let's say 2500 ml VSS is what you would have or is fine, okay. So theta is the hydraulic retention time, keep that in mind, it is not the cell residence time. So as you see, the theta hydraulic retention time is much lesser, theta C obviously around the range of a few days, let's see, right. So that's something to keep in mind. Okay, so with a large basin and smaller X, what can you achieve? So improved effluent quality and lower effluent suspended solids. In general, for a well-run treatment plant, you will still have some BOD leaving the system, but that's not due to BOD that is soluble, it's BOD that's relatively suspended, let's say, right. So you would want to bring down that effluent suspended solids. But if the basin is too large and leading to X being very small, then difficulty in removing the relevant organics and also leading to poor thickening, let's say, right. Again, we are not going to discuss this. So simple models, how are we going to go about it? Choose values for the primary design variables. What are they? Obviously theta C, and limiting substrate removal, how much do you want to remove? Based on that you can choose a safety factor. So soluble BOD5, most BOD5 in effluent is due to suspended solids, as I mentioned earlier, and you will look at the ammonia nitrogen, the oxygen production that is required. Obviously it increases with greater theta C, and then the amount of sludge that is being produced, let's see, right. So effluent limiting substrate concentration, this is something that we got, right, based on the relevant mass balance. So we applied the mass balance and we also looked at the equation where we had rate of R net X is equal to our rate of production of X minus rate of loss of X, substituted relevant aspects and we came up with this, right. So based on the laboratory data, you can have these kinds of information, mu max, Ks, Kd and such. So based on that you can calculate S, or given S, calculate the theta C, let's see, right. And then if HRT, you can calculate that if X is assumed, or if biomass concentration also can be calculated if HRT is assumed, right. So for that That is what you have here, right? Earlier based on S you can calculate theta C, and now if X is given you can calculate theta, if theta is given you can calculate X, right? One or the other. Typically you will choose the hydraulic retention time because that will what do we say, give an idea about the volume of the relevant tank, let's say, right? Well, not only HRT, that will give you an idea about what do we say, the flow characteristics too. So that's something you need to look at it, right? So mass flow of biomass required, right? Px, we looked at this. So this has to be a minus as we discussed earlier. So this is also required. Why? From that you will have to calculate the mass flow of oxygen. So we looked at S equation, we looked at X equation. S is a function of theta, X is a function of theta and theta C, right? And then we are calculating Px, right? And then we will calculate the mass of oxygen, right? General steps out there. Again, depending on what variables are given or not given, you will have to play around, and depending upon what do we say, the assumptions that we made, maybe we might change the assumptions or let's say we might choose other assumptions. So you might have to change the mass balance a bit. But again, please note that the mass balance, there are only two aspects. This is a CSTR, and we either apply the mass balance around the entire system for the substrate and the microorganisms. If we want to look at the ratio of recycle, how much I need to recycle, what do I need to do? I need to look at the relevant mass balance around the clarifier on the biomass, let's say, right? So from that and your relevant mono equation kinetics, you can get whatever it is you want. So it's all about mass balance, right? So then you will be able to calculate the mass flow of oxygen required for S as BOD. We look at the oxygen requirements. So actual oxygen transfer rate, right? Volumetric flow of air, we already know how to do that. In that AOTE or AOTR, you know that you need to calculate C average, right, based on the pressure, right, at that particular depth to the atmospheric pressure and the oxygen leaving the system, right. So this is what we have. Based on that you will calculate C average, let's say, right. And then I guess you can calculate AOT and so on and so forth, and you will calculate the airflow, total airflow that's required from this, right. You have the mass of oxygen required and you know these variables, and thus you can calculate the required airflow. So the number of diffusers obviously will depend upon this total airflow by the airflow at standard conditions or per diffuser, let's say. So different kinds of diffusers. So every aeration diffusers on the right, the flow control wear out here so that you have relevant outflow, right. So again, different kinds of diffusers. Let me see if I have a better diffuser. So here looks like they choose these kinds of aeration systems, especially on one side, so that there is a spiral roll or good mixing as it goes along, what do we say, passes through the tank, let's say. Okay. So diffused aeration, so this is what we have. Cross section of a typical aeration tank illustrating the spiral flow pattern created by aeration on one side, right. So you have this spiral flow, at least if not along the flow direction, perpendicular to the flow direction, you want to have good mixing. So that's what you are going to achieve, and with that again you are going to have what do we say, forward movement, let's see, right. So calculations, mechanical aeration, power of mechanical aerators, we know that. Again, actual efficiency with respect to standard efficiency, where we look at the power or the energy requirements. We also looked at the relevant, what do we say, formula. And what do we have here? Total power required is the mass of oxygen by the efficiency or actual power per aerator. So again, total power by standard power per aerator into AE by CE. So again, these are all very general, what do we say, pieces of algebra, just fractions and so on and so forth, right. So in summary, if Q is there, the flow rate of the concentration of flow rate of the wastewater and the concentration of the wastewater, right. And regulations will typically give you, if not efficiency, what is the outlet. For example, in the plants discharging into Ganga, we know that the effluent BOD should be less than 10 milligram per liter. And from bench scale studies, what are you going to have? You are going to get the yield coefficient, half maximum, and I guess mu max, sludge volume index. Sludge volume index will give you an idea about how well the sludge is settling. And then safety factor or theta c and x can be chosen upfront based on the kind of system that you want to have. And then you will calculate for P, right, mass of or biomass production, let's see, right. So, with that I am done with, more or less done with design. So, in the next session we will look at different kinds of activated sludge process, and I think we will look at a video so that we understand the system in practical terms, let's say. And coincidentally I am also out of time. So, thanking you for your patience. I will end today's session.